Okay, turn to number 7. Turn to number 7, please. Turn to number 7. 7. Okay, I'm looking at 7C specifically. 7C. Okay. Listen close to the following words. Estimating about estimating the value of an integral with a trapezoidal Riemann sum. There's 4 different types of Riemann sums you'll be asked to estimate. On the actual AP test, they probably won't ask you about all 4. You just don't know which they'll ask about. So you have to be prepared for any of them. The idea is really simple. We've already talked about left, and we may have talked a little bit about right. For example, here, they say approximate this integral. So you've remembered that every time you are using an integral on the AP test, you want to make sure you write the integral, because they often will take away points if you don't. Caution. You've got to be good with your notation, because this is the written section. Unlike most high school classes, when the teacher grades a test, they just kind of glance at the work and like, it looks like you got most of it, and they give you points. On the AP test, they look very closely. So your test will be graded in the same way, like close grading. It takes a long time. You can't, like I've seen people do this. They write an integral sign and then they write equal. That's like writing plus, equal. Like it doesn't mean anything. You can't just, that makes no sense. So, we are integrating v of t dt. The other thing you should always do is, again, don't just do work, think as you're working. So notice that you're multiplying velocity by time. So just do a little test to make sure this is making sense. Velocity in this case is feet per second. dt means change in time. That will be measured in seconds. So as expected, the integral is going to calculate some number of feet, because the integral is calculating displacement. Question? Cool. Okay, it says trapezoidal Riemann sum with these subintervals. So another thing they're changing is how the subintervals are specified. So I'm going to go from time 0 to time 20. Or up in the table, I'm going to go, oh, remember, don't do this. I've already had 2 people come to my desk on a homework problem and say, the problem just doesn't work. And the error they're making is they draw lines like that on the table. We want to start at time 0 and go to time 20. Then we want to go from time 20 to 30. Then we want to go from 30 to 70. Okay, questions regarding the subintervals? Okay. So 4 types of Riemann sums: left, right, trapezoidal, and midpoint. On a left Riemann sum, you look at the interval and you pick the time that is most left. Right, you pick the time that is most right. Midpoint, you pick the time that is in the middle. Question? Okay, trapezoidal is the one that is a little different. You actually pick the left and the right. So this is going to be, time on the left is 0, Time on the right is 20. You add those two velocities together, and then you multiply by 1/2. So talk to each other, raise your hand, and tell me. When I take two velocities, add them together, and multiply by 1/2, what am I actually calculating? Hands, please. With regard to the velocities, what's being calculated when you take two velocities, add them together, and multiply the sum by 1/2? With regard to the two velocities, what is being calculated, Britt?
The midpoint between the velocities.
2 points. Where do we want to use as average, to be fair?
Okay.
No worries. I see why you would say maybe midpoint, but we'll just, average is technically more correct. So how many do it? 0.2 per bit. So the trapezoidal is actually an average of the left and the right. So that's this part here. That's the V of t. We still have to multiply by dt. So I look at the first subinterval and I say time changes by an amount of 20 minutes in the first subinterval. So this gets multiplied by 20. Question? Reminder, all you're doing is calculating displacement because this is a velocity. It's the average of the left and right velocity. So if I take a velocity and I multiply by an amount of time, I'm calculating a displacement for that time period. That's what we're doing. Question? Then we just repeat for the other subintervals. So of 1/2, this would be V of 20 plus V of 30. Any questions to there? So that's how we calculate the velocity for that subinterval. Raise your hand, I'll pay you. What's the dt for that subinterval, hand? What's the dt for that subinterval, Allie? 10. How many agree? 2 points, 3 for Allie. And then we finish with the last subinterval. Questions? We want to talk about any part of it. Sweet. Okay. If you look up at part A says use the graph to illustrate the trapezoidal Riemann sum approximation. What would it look like visually on the graph? So what you do is, again, look at the subinterval, and we are taking the width of the subinterval. We're also taking the velocity on the left of the subinterval and the velocity on the right. It turns out that this little formula this formula times the width of the subinterval is the same as a formula for finding the area of a trapezoid. So this computation is finding the area that I am drawing in red. So the area that I drew in red, that's the area that is computed by this computation. That's why it's called a trapezoidal Riemann sum. Question? Because it makes a trapezoid. Now, ideally, if we could make the intervals really, really short, so there's lots of subintervals, you'd have a bunch of tiny trapezoids, and they become so narrow that if they became infinitesimally narrow, you would no longer be calculating the area in red. You instead would be following the curve perfectly. And you'd be calculating the area in green, as best I can draw. So just say it out loud, please. Which is larger, the green or the red area? Green or red? Louder? Yeah, that was a really bad choral prompt, my bad. So the green is bigger, right? The green is the ideal. If we could do the integral perfectly, we would find the green area. We're finding the red area. Therefore, our trapezoidal Riemann sum is an underestimate. We want to talk more about that. You're good. So, kind of went fast through that. Let's do a little bit slower. So you're okay that this computes the red area. So I had that drawn. If I shorten, like if I have more subintervals, you're going to get little trapezoids, kind of like this. And then another small trapezoid. Y'all signed up for the wrong class, sorry. Look. If you make the subintervals narrow, you get narrow trapezoids. It's hard to draw, so you kind of have to imagine. But if you can make the trapezoids narrower and narrower and narrower, their shape gets better and better at following the actual shape. If I exaggerate what I'm saying, it tends to be a little easier to see. Like, here's some sort of graph. And if I make a trapezoid that's pretty wide, like so, pretty easy to see that the area of my trapezoid is significantly less than this area. Agreed? Good. But if I make the trapezoids really, really narrow, they get pretty good at following the curve because they're so narrow. And this is where you have to kind of imagine. If you could make the trapezoids infinitesimally narrow, they would follow the curve perfectly. So the perfect integral would find the area between the x-axis and the curve perfectly. So my estimate is definitely too small. 2 points. There you go. Any questions? Okay, throughout this packet, they're going to keep asking you, is your trapezoidal Riemann sum or your right Riemann sum or your left Riemann sum, is it an over or underestimate? Best way to calculate that is just draw a picture. Like draw a picture of what you are calculating compared to the ideal. The ideal being, like I said to KLA, if the rectangles were, like if the shapes, the trapezoids or rectangles were so narrow, they would follow the curve perfectly. How does your shape compare? Question, please.
Wouldn't you just say if you were trying to get down, it's always an underestimate, and it's trying to get up, and it's always, well, yeah, it's always bigger.
So everybody listen to Cameron. If you're finding a trapezoidal Riemann sum, you can simply notice that. It works perfectly. If I have a graph, and the graph I'm integrating has a concave up shape, when I create my trapezoids, as I do my Riemann sum approximation, those trapezoids are going to compute an area that's too big, always. Perfect. Question? Now where it gets harder, it's not harder, but they ask the same question with like left Riemann sum and right Riemann sum. like this one's pretty fast. Trapezoidal Riemann sum. If the curve is concave up, then my estimate's too big. It's an overestimate. If the curve is concave down, then my estimate will be too small. That's pretty easy to memorize, and you can see it visually really quickly. I struggle with these two. Like there's 4 rules you'd have to memorize for these. And because there are 4 of them, they just get mixed up really fast. So I found it better to just draw a picture. I say, okay, if F looks like this, and in this case, it doesn't have to do with the concavity. It has to do with the increasing versus decreasing. So if F is a increasing function, and I pick a subinterval, and I take the velocity on the left, well, I'm going to be finding this area too small. So I'd be computing an underestimate. So that means if it's a left Riemann sum and the function is increasing, that's an underestimate. But if I were taking the same function and I pick the velocity on the right, well, now my approximation computes the area in green, which is too much. So that means if I'm doing a right Riemann sum, function is increasing, now I've got an overestimate. So I don't typically try to remember the rule, I just draw a quick picture. Anybody else? Cool. Back to here. Okay, let's stop that one.